Welcome back, AP Calculus AB, to our third targeted review. This targeted review is on tabular data, which we've actually done a lot of. So I figured we could also use it to review a couple theorems and just kind of some weird problems that you might not see as much. There should mostly be problems that we haven't seen in the last 2 days, and it's a nice, easy way to check and see where you are. The first problem is no calculator. The second problem is calculator active, so you'll want to make sure you have a calculator available for you. I'd like you to take 30 minutes. You should be able to work through the first or both of these problems, see what you can do, and then at the end of 30, come back and see how you did. Other than that, we don't have much else to discuss for today. As a reminder, tabular data is just data that's presented in a table. So you'll see data in a table there and another one down here. It's a very common question. At some point, one of your 6 free responses, maybe more than one, is going to present data in a table, and you'll be expected to analyze it using calculus. So take those 30 minutes, and once you're done, come back together and we'll see how you did. Ready, set, go. All right, well, let's begin. Explain why there must be a value r for r between 1 and 3 such that h of r equals -5. Well, I'm looking at an equation h of x and a guarantee for h of r. This is one of those weird ones where we're not actually going to be doing any calculus here. This is a theorem, right? Explain why, explain why. In fact, I think both of these are going to be theorems. Just a friendly reminder of the 5 or so theorems you really need to know. I guess maybe there's 6. The very first theorem we learn is the IVT, the intermediate value theorem. And that's something like, if you're given, we'll use this as an example, h of x, then guarantee something about h of x. The next one we learn is the EVT, the extreme value theorem. They, I think, would be pretty hard-pressed to test you on the free response section on the extreme value theorem, but just a friendly reminder that the extreme value theorem just guarantees that if you have a continuous function on a closed interval, there will be an absolute max and an absolute min. Right? It's just guaranteeing at least one absolute max, at least one absolute min. Wouldn't expect to see that on the free response, but multiple choice possibly. We also learn the MVT, and that's something like, given h of x, then guarantee or explain why or tell us how come something about h prime of x. Fourth one is our average value theorem. Not really a theorem, but that's our formula, right? 1 over b minus a integral from a to b of f of x dx will give you the average value of f of x. So given f of x, it tells you something about f of x, or h of x. The fifth one that we need is the squeeze theorem. Not very commonly tested, but one of our free responses down the road will remind you of how that one works, but just a quick heads up before you get there. The squeeze theorem guarantees the value and the existence of a limit if you know 2 other functions, one above, one below, and their limits as well. And then the last one is one that we really need to know. It's our fundamental theorem of calculus. There's part 1 and part 2. Depends on your books. Part 1 just says if you're doing the antiderivative of f of x dx from a to b, it's capital F of b minus capital F of a. Right? And then part 2 tells us if you're taking the derivative of, I don't know, let's do a nice intense example of something like 2x to x squared of f of t dt. These essentially cancel, but then our fundamental theorem, if you do the antiderivative, x squared gets plugged in, and it becomes f of x squared times the derivative. That's our chain rule. But then from this fundamental theorem up top, we kind of took care of the f of b piece down here, but then we need to subtract f of 2x, the bottom one, right, and multiply by the derivative of that guy. Easy enough. If this was just a 2, then it'd be f of 2 and the derivative of 2 would be 0, and that would all cancel out. So usually we just say you just have to worry about if there's a variable. If it isn't a variable, you don't have to write it, but don't forget there is a minus kind of separating everything through. All right, so now that we have a brief reminder of those, let's put them into practice. Explain why there must be a value r such that h of r equals something, and we're given h of x. To me, this must be the IVT, right? We're given a function, we're asked something about that function, so let's get to it. The way the IVT works is we have to find the starting output and the ending output. Starting output, h of 1, that's going to be f of g of 1 minus 6. G of 1 we can find through the table, right? G of, whoops, that's 2. G of 1 is 2. And then we have to find f of 2, and f of 2 is 9. So we end up with 9 minus 6, which is 3. Not bad. Ultimately, we found that we start at the point 1, 3. Then we also need h of 3. F of g of 3 minus 6. G of 3 is 4. And then f of 4 is negative 1, which is negative 7. That gives us the point 3, negative 7. So I would probably not make a graph here. You can if it makes you happier, but we just need to realize that negative 5 falls in between 3 and negative 7. Right? If you wanted a graph, and I said you didn't have to make one, I just wanted to show you a visual. If we're starting at the point 1, 3, and we're ending at 3, negative 7, the graph can do whatever it wants between here, right? But it has to eventually get down there, which means eventually it's going to have to cross over negative 5, right? Does it really have to, though? Could it go down here? Could there be an open circle and then it finish off? Well, let's see if there could be an open circle. Functions f and g are differentiable, and notice that h is made up of differentiable functions minus a single value, and so we need to remember that f and g are differentiable, which means f and g are continuous, which means therefore h is also continuous. In fact, I'm going to state that right now. The year that this came out, maybe 2008, something like that, this was one of, if not the lowest scoring free response question in the history of the AP exam. I think the average student got 0 points on it, slightly less than 1, because there were a bunch of theorems and there were some really tricky questions. They were not very picky about how this answer was written, and so I'm actually going to write how most of us would probably put this answer, and then I'm going to amend it right above. So I'm going to leave a little space right here, but I'm going to write my answer down below. So here is how normally I would probably write this. I would say something like, as h of x is continuous on, and we always do the closed interval, so on 1 to 3, and differentiable on the open interval. That's just our, kind of our prefix every time we're going to do this. And you can do this on any problem if you want. But continuous on the closed interval, so include the endpoints. Differentiable, there are slopes that exist between these. And actually, the differentiability part is not useful here. I'm getting ahead of myself to the next one, so we'll just do continuous on a closed interval. And notice this guy, right? So we're going to have to talk about this one. The smallest value came from when we did h of 3, didn't it? So h of 3 is less than negative 5, which is less than h of 1. Just showing that negative 5 is in between these two values. Then the IVT, and then the rest of it is just rewriting the question. So then the IVT explains why, and I'll actually write the whole thing out, normally I don't, there must be a value r for 1 less than r less than 3 such that h of r equals negative 5. Done. Now this last year, just this last year, so this would have been in 2020, they did not accept this for full points. And the reason they didn't accept this for full points is because they mentioned that f and g are differentiable, but nowhere in here does it explain continuity. So this last year they were very, very picky about you making the connection between differentiability and continuity. And so you actually had to state last year something like, as f and g are differentiable, then f and g are continuous. And I'll even go further, and thus h of x is continuous, and I'll even put n differentiable. Why not? So if you didn't state this part, if you didn't explain how you knew the function was continuous, then you did not get full points on this. And so even if you're like, but I know differentiability means continuity, what they were checking last year is to make sure that you didn't just memorize a definition and say, oh, we always just say continuous, even if the problem doesn't necessarily state continuity. So be very careful about that. If they tell you f and g are differentiable, specifically state the link that because they're differentiable, it means that they're also continuous. All right, moving on through. Explain why there must be a value c such that h prime. Now, there are two ways to do this. One way they made very carefully sure wouldn't work for you. So I'm actually going to do the way that doesn't work first. You might look at this, say, this is h. They're asking about h prime. So I'm going to use the IVT. In order to use the IVT, we need the same equation, h and h. So if this is h prime, I need h prime. So students will find h prime of x. And you might not want to write this because I'm going to erase it. F prime of g of x times g prime of x, and then the 6 becomes 0. And then they find h prime of each of these values. So they find h prime of 1, and let's quickly do this one. Let's see, g of 1 is 2. There we go. F prime of 2 is 2. G prime of 1 is 5. 2 times 5 is 10. Okay. And then they also find h prime of 3. So this becomes f prime of, let's see, g of 3 is 4. Let's see, f prime of 4 is 3. G prime of 3 is 2. That's 6. Okay, so they find these two. And then they look at them and go, ha! -5 isn't between those two, so we can't explain why. Well, there's two things wrong with that. First, it says explain why there must be a value. So there must be a value. They're not lying to you. They're not saying explain why and you have to say, ha, the AP exam's wrong. There isn't. And second, you're making a false assumption about the IVT. What's happening right here is if we start at the point 1, 10 and we end at the point 3, 6, you're saying they must go right here. Which you're not necessarily wrong. You must pass through all the y values from 10 to 6. But is there anything saying that you couldn't swoop all the way down and go by -5? Right, the IVT just guarantees that these values in between the two outputs happen, but it doesn't tell you anything about the fact that other outputs could also happen. And in this case, there are other outputs that could also happen. Now, if this happened and you went through and tried that IVT, you would hopefully say, oh, drat, we need to approach this another way. Now, another reason I was pretty confident you wouldn't use the IVT here is the AP exam only has about 24 free response short answer questions to test you on an entire year. If they already tested you on the IVT once, they're not going to do it again. It is very uncommon for them to ask for the same theorem more than once on an entire free response section. So to me, this means a different theorem. In particular, this is our MVT. We have H. We want to guarantee something about slopes. What's our setup for the MVT? Well, the first thing we want to find is the average rate of change. Average rate of change. The average rate of change will be H of 3. Notice H, not H prime, minus H of 1 over 3 minus 1. This is like the slope formula for H. The slope of H is H prime. So this is telling us something about H prime. We've already found H of 3 and H of 1 earlier. H of 3 is -7. H of 1 is 3. And we get -10 over 2, which is -5. All right, we found that average rate of change because they match. We are in business. How do we conclude? Very similar to the other one. As h of x is continuous on 1 to 3, that's the closed interval. This is what I tried to do last time, and differentiable on 1 to 3 on the open interval, and the average rate of change is -5, then the MVT explains why there must be a value C for 1 less than z less than 3 such that h prime of c equals -5. Woo! Look at that. Go us. Mean value theorem. Some people say, well, instead of average rate of change, could I say like slope of the secant line? Sure. Slope of the endpoints, yeah, that's fine as well. Nothing wrong with that. But just making sure that you establish what you found up here. Sometimes you can even get away without doing that, but it's always nice to explain what you found, right? Remember, the MVT says that if you find the slope between the two endpoints, then there is guaranteed to be some other spot in between the endpoints that will have that same slope or same derivative. All right, moving on to some actual calculus instead of theorems. Let W be that. Find the value of W prime of 3. Oh, I found so many people in the past for this problem. They say, oh, W prime of 3, let's plug in 3 and then take the derivative. You can't do that. In order to find W prime of 3, the first thing you need to find is W prime of x. How do we find W prime of x? Well, we take the derivative of the original equation. So this first step, again, is optional, showing this ddx. I always like to show it, though, just so you can keep track of where everything came from. 1 to g of x, f of t dt. The derivative of wx is w prime of x. This guy, oh, we talked about this one. This is the fundamental theorem, part 2. G of x goes in, these cancel, we don't do anything to f. So f of g of x, chain rule, times g prime of x. All right, let's finish this off. W prime of 3. That's got to be f of g of 3 times g prime of 3. All right. What is g of 3? G of 3 is 4. All right, so then we need f of 4 and g prime of 3. F of 4 and g prime of 3. That looks like -1 and 2, which is -2. Go us. Last but not least, if g inverse is the inverse function of g, write an equation for the line tangent to the graph of g inverse of x at x equals 2. Okay, well, let's start this out. We've done tangent lines before. We know we need the derivative of g inverse at 2. Now we have x minus 2 plus g inverse of 2. Right? We're writing all this out because they asked us to do it to the inverse function. Okay, well, some of this isn't bad at all. G inverse of 2 is actually what I'm going to start with because we'll need that later on. To find g inverse of 2, then we might, and I actually usually make a couple tables over here, saying we are inputting something. In this case, we're inputting 2, and we're trying to find the output. But if you're unsure of that, don't forget that we can always look at the original function and say, okay, well, instead of looking at the inverse, which we don't know a lot about, let's look at the original. And what is the relationship that an inverse coordinate pair has with the original function? It's that we can switch the 2 points, right? 2 comma something means something comma 2. And we can determine that just by looking at our table. When is the output 2, or what x gives an output of 2? So we're looking at g of x. Are there any outputs of 2? Yeah. It looks like an x of 1 gives an output of 2, which means then that an input of 2 into the inverse gives an output of 1. So we know that t of x equals, I'll leave a space for the slope, x minus 2 plus 1. Last but not least, we actually need to find the derivative of the inverse, and although you can derive this formula if you would like, it's one that you should know at this point. You've practiced it enough. The derivative of the inverse of 2 is 1 over g prime of the inverse of 2. So what is the inverse of 2? The inverse of 2 is 1. And then we need 1 over g prime of 1. G prime of 1 is 5. And we're here. There is our tangent line. Yeah, definitely a tricky question. Lots of theorems. Really, the first 3 parts are theorems, and the last one is the derivative of an inverse. Really, really tricky. If you know them, they aren't too bad. But if on any one of those you're like, oh, I don't remember that part, I'm a little weak on theorems, then it's definitely a tough question. Brush up on those theorems. We've done a couple classes on theorems. Look back through the videos. And for now, let's go ahead and hit our second problem. this one should go a little faster. Temperature of water in a tub is modeled by a strictly increasing function w of t. Time t equals 0, the temperature of the water is 55. Water is heated up. Ah, nice. Warm bath. Love that. Or hot tub, I don't know. For 30 minutes, beginning at a time of 0. Values of wt are given in the table below. Okay? Use the data in the table to estimate w prime of 12. Show the computations that lead to your answer, and then interpret your answer. Okay, we've done this before. 12 would be somewhere in here between 9 and 15. In fact, 12 is exactly in between 9 and 15. It's the average of those two. Even if it wasn't, if they asked you to estimate w prime of 11, you would still use this same idea, where you want to go ahead and you want to find the, we'll say, air quotes, slope, end quote, between these 2 points. You always pick the two closest, one above, one below, if you're asked to estimate. So capital W prime of 12 is going to equal, well, sorry, not equal, we're estimating, is approximated by W of 15 minus W of 9 divided by 15 minus 9. W of 15, 67.9, W of 9, 61.8, all divided by 15 minus 9, which I'm pretty confident is 6. Now, I've mentioned before about not simplifying. This is a calculator active problem. So you have two options here. Option 1 is you put all of this into your calculator and you get the right answer. Option 2 is if you're feeling not optimistic, stop right there. This is acceptable as an answer. That is something I could type into my calculator. Now, I will go one step further and I will put the answer, and I'm going to do it on my calculator, take my own advice. But again, if you're unsure, even if it wasn't calculator active, if you're unsure on your decimal subtraction, just stop. Leave it right there. That's full points. So here we go. 67.9, 61.8. Let's see. Calculate. There we go. 67.9 minus 61.8 over 15 minus 9. And for this one, I'm going to show you both of these. If I hit enter, oh, I do get a decimal. Okay, I wasn't sure if it'd give me a fraction or not. 1.016. Okay, what about my units? Well, W has units of degrees Fahrenheit, and T has units of minutes. So I see degrees Fahrenheit per minute, degrees Fahrenheit per minute. Right? Let the table guide you. Okay, from here we do need to interpret the meaning of our answer. So, same thing before. W of t, and we're going to explain what W of t is, right? The temperature of the water, hence W, right, in the tub is changing, right, because a derivative right here always measures the rate of change, is changing at t equals 12 by, and it's always at, it's not during, it's not over, it's at. A derivative talks about what happens at a point, at t equals 12 by 1.016 degrees Fahrenheit per minute. Pretty easy sentence right there. You explain what you're looking at the change of, and then you're explaining how that thing is changing. Using the data in the table, evaluate 0 to 20 W prime of t dt, use correct units, interpret the meaning. We can do this. Sometimes I see people look at this and say, oh, I should use a Riemann sum right here. A Riemann sum is going to be really useful. If they don't say to use a Riemann sum, don't use a Riemann sum. Right? There's nothing here that says on B, use a Riemann sum. You can't just arbitrarily pick. That means there's a different way to do it. Remember, a definite integral has two ways to be evaluated. The first way is using area. That's like a Riemann sum. But the second way is just to use the fundamental theorem, and I think we can actually do that here. The integral from 0 to 20, capital W prime of t dt, by the fundamental theorem, isn't that W of 20 minus W of 0? We do the antiderivative first and then substitute those in. And I think W of 20 and W of 0 can be found up above. W of 20 is 71. W of 0 is 55. Again, if you're not comfortable, if you ran out of calculator time or something, just leave this as your answer. But if you want, you can do that on your calculator and you'll end up getting 16. Okay, 16 what? Let's look at those units. W prime of t. We just found a W prime up above. That's degrees Fahrenheit per minute. The change in time, that's minutes. Cancel. It looks like we're at degrees Fahrenheit. The other way you could have seen that is you could have realized you're subtracting two W values. If you subtract degrees Fahrenheit and degrees Fahrenheit, you still have degrees Fahrenheit. What is the meaning of this? Well, when you subtract two values, you're looking at the difference in them. So we're looking at the difference in the temperature from a time of 20 and a time of 0, right? So the W of t is the temperature in the bathtub, right? The temperature of the bath water has changed by 16 degrees Fahrenheit from t equals 0 to t equals 20. You could say increased because it's positive. I just find changed is a little bit easier, but totally up to you. That's it. Riemann sums. Use a left Riemann sum with the 4 subintervals indicated by the data in the table to approximate the average temperature of the water. Does this approximation overestimate or underestimate the average temperature of the water? Explain your reasoning. Okay, left Riemann sum, approximate. So we have W of t. Let's get to it. We have the integral from 0 to 20, capital W of t dt. We're measuring the area underneath W of t. Left Riemann sum. Well, we have these intervals up here. Let's look at each of these subintervals. Here's our first one, right? Let's use circles this way. Here's our first interval, then our next one, and so on and so forth. I think I have just enough colors to make this work. Oh, even more than enough. The first interval. So if you're thinking about a graph, and when in doubt, draw a graph. You're going to have enough time on the free response. Draw a graph. 0 to 4. That's our first subinterval. The base is clearly 4. The base is found by subtracting those two values. The height, we have to pick from one of these two, right? We're going to pick. We're not doing any weird subtraction. We're finding the height. And this is a left Riemann sum, so which do I choose? Oh yeah, the one on the left. So my first one is going to be a base of 4 and a height of 55. And then we continue on. In this green one, we're going from 4 to 9. So how long is the base? The base is 5. Subtract those two. Base of 5, height of 57.1. 57.1. And so on and so forth. I need to zoom out to see the rest of these. My third one is going to be from 9 to 15. That's a base of 6. And then I'm choosing the left, so 61.8. And last but not least, we have a base of 5, and we're choosing the left, 67.9. I probably should have made these approximately's because we are approximating, and we're good. Now, full disclosure, if you stop right here, if this is your answer, you receive full 100% credit for the first part of this problem. Because they asked you to use a left Riemann sum, this is an answer. If this was a non-calculator active problem and you're like, I don't want to do all that multiplication and add them up, then don't. Stop right there and you'll get full credit. Now, a couple things to note. This is calculator active, so I am going to go ahead and do all the math. And then once I've done all the math, we are going to go ahead and check out those units and see if we've answered the full question. So let's see here. We're going to minimize this so I can see everything. 4 by 55 plus 5 by 57.1. There we go. And one more. 67.9. Awesome. 1215.8. Okay. So this integral is 1215.8. Let's check those units. Unit-wise, W of t was the temperature of the water, that was degrees Fahrenheit, and dt, the change in temperature, the change in time, t, temperature, time, okay, the change in time was minutes. I'm getting an answer of degrees Fahrenheit minutes, not per minute, degrees Fahrenheit minutes, and that is a pretty nonsensical unit. If you get nonsensical units, you made a mistake, and we need to do a closer read of the problem to understand where we went wrong. Use a left Riemann sum with 4 subintervals, did that, indicated by the data, did that, to approximate the average temperature. Average temperature means my final units need to be temperature. They need to be degrees Fahrenheit, not degree Fahrenheit minutes. How do we do the average temperature? Well, if this is the temperature and I want the average of that, then I think I need that 1 over b minus a. This is like an average value problem. I need the average here because this guy is in 1 over degree Fahrenheit. Nope, this is time. 1 over minutes, which will cancel out the minutes and leave us with Fahrenheit. I find sometimes students recognize that at the end when they're like 1215, that is way too big to be the average temperature of the water. They would be really, 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 really warm water. I think that'd be steam, actually. So they realize that at the end, and then they go, oh, wait, I need to divide by 20, and then they get their answer. You would not get full credit for that because this integral is not equal to 1215 divided by 20. Right? In order to get full credit here, we would need to carry over this divided by 20 or put this 1/20th in the front of everything here. We cannot say two things are equal if they are not equal. Now you can put it over 20 if you'd like. But if you realize at the end you need the 1/20th, put it everywhere to make sure that we're consistent. So I need 1215.8 divided by 20. Easiest way to do that is just do divided by, because it'll take your answer, by 20. And we get 60.79. I'm suspicious, but I shouldn't have been. It is 60.79. I was checking for those extra decimals. So 60.79 degrees Fahrenheit. And then we check. I mean, does that make sense? If you look up here, does it look like the average temperature is somewhere in the 60s? Sure, we went from 55 to 71. Average temperature in the 60s makes sense to me. Sweet. Does this approximation over or underestimate the average temperature? That always comes down to the Riemann sum piece, and I never remember how to do this, so I always sketch myself a little graph. And I know it has to do with increasing, decreasing. So strictly increasing function w. W is positive and increasing. So here's a positive increasing function. Then we did a left Riemann sum. So I just set up a couple intervals. Okay, first interval right here. To do a left Riemann sum, I make an L, right? That's a left. And then the rest of this we go over. Okay. If I do this next one, we make an L and then go over. So if you think about the areas accumulated between these two rectangles, do those do a good job of finding too much area or too little area? Well, the actual area would fill in these pieces as well. Looks like a left Riemann is an under approximation. How do we state that? As W of t is positive and increasing, our left Riemann sum under, I'll start right over, under approximates the average temp. Great. Easy enough. What do you need to include there? You need to explain that W of t is positive increasing and that you used a left Riemann sum. So a lot of times I see students say WT is positive and increasing, so it's an under approximation. But that's not true, because you can have a positive increasing function that's an over approximation. Imagine we had this same thing again, but instead of doing a left, we did a right. If I do a right, that would be an over approximation. It's only the combination of increasing and a left that makes this an under approximation. Okay, last but not least. For 20 to 25, the function w models the water temperature. First derivative given by an equation. Based on the model, what's the temperature of the water at the time? Well, this is a derivative. We know the units that a derivative has, degrees Fahrenheit per minute, and they're asking us about temperature, degrees. How do we go from degrees Fahrenheit per minute to temperature? We do the antiderivative. All right, so we need to do the antiderivative from, well, from what to what? Definitely 25, and since it says from 20 to 25, that probably seems like we're going to do 20 of w prime of t dt. But we don't just want to put this into our calculator, because this answer won't tell us what happens at a time. An integral always tells us what happens over an interval. This is going to sum up how the temperature has changed over these last 5 minutes. Yeah, over these last 5 minutes. So how do we find what happens exactly at a time of 25? Well, we need to remember that fundamental theorem. It becomes W of 25 minus W of 20. We want to know what happens at W of 25, so let's manipulate that fundamental theorem. Add W of 20 to the displacement, right? That's what this change in temperature is known as. It's our displacement here. And that should tell us our temperature at 25. W of 20, though, you might say, oh, how do I find W of 20? We don't have the equation for W. Oh, it's up here. W of 20 is 71. They gave that to us. Sneaky, sneaky. How do we find this? Well, that's all about our calculator. So calculator-wise, we need to put all this in. I see a trig function. Make sure you're in radians instead of degrees. And let's go ahead and take a look. So we're going to clear this guy out. Menu, calculus, integral. We're going from 20 to 25. And then I don't have this function built in. It was 0.4 times, I don't know, square root of something, I think. Maybe the square root of x. And then make sure you get out of that square root. And let's see how bad I screwed this up so far. 0.4 square root of x cosine of 0.06x. Trig cosine of 0.06x. There we go. And I used x all the way through. Could you have used t? Certainly. There's nothing wrong with that. Just make sure it says dt at the end. Hit enter. 2.043. 2.043. I usually put ellipses at the end just so you can see that really does go on forever, and then we're going to add those together. So that plus 71, I'm just going to do plus to copy the answer. 71, there we go, 73.043. Guess I probably could have done that with some mental math. Whoops. There we go. And we're set. So yeah, these tabular data problems tend to not be too terrible. They love asking you to do an estimate when you do. This is essentially an application of the mean value theorem. They sometimes try and trick you by making sure you remember the fundamental theorem. Left Riemann sums or rights or midpoints or trapezoidals come up a bunch, but nothing too crazy. They're pretty predictable on what they're going to ask. Sometimes, though, they can throw you off, like this first tabular data asked all about theorems and the derivative of an inverse. This almost always shows up on the multiple choice, not the free response. It will show up somewhere. Usually only once, though. It's not that important of a topic, but you do need to know this formula. It pops up at least once each year, so make sure you don't miss some fairly easy points. Thank you for joining us today, and I'm excited to have you guys back next class for a review of particle motion.